Okay, let's talk about how the central limit theorem applies for proportions. First of all, our little reminder, a parameter is a numerical summary of a population, and statistics a numerical summary of a sample. We've so far mostly talked about the mean and the standard deviation. So now we're going to introduce a new type of parameter and the new type of corresponding statistics. And so this time the parameter that we are interested in is the population proportion, which we usually indicate with a lowercase p. Okay, and so this is going to be a fraction or a percentage written in decimal form of the population that possesses some characteristic of interest. For example, we may be interested in the proportion of children who have a certain medical condition, or U.S. citizens who got a tax refund. There are all sorts of things. U.S. citizens who are unemployed, so if the unemployment rate was 5%, that would be a proportion of 0.05. So that's examples of what would be a proportion that we might be interested in. Okay, and then the sampling distribution of the sample proportion is, for a fixed sample size of n, all the possible values that you can get for a sample proportion taken from a population. Okay, so if you have a population that has a certain proportion of whatever characteristic, and then you grab random samples of, say, 20 over and over from that population, then for each of those samples of 20, you could calculate what proportion of the 20 has the characteristic. And then if you throw all of those sample proportions in together, then that's the sampling distribution of the sample proportion. And we call the sample proportion, we indicate that with a lowercase p with a little hat over it. So we call this p hat. If we're speaking about it in words, we'll call it p hat. But if we write it as a p with a little party hat on top. Okay, so then how do we actually get that sample proportion? So what we do, and we've done this sort of thing before when we talked about frequencies and relative frequencies, we take the number that have whatever characteristic we're interested in, and we divide it by n. So if we had a sample size of 100, to make the calculations easy, and say 40 of them had the characteristic, that would be 40 over 100, or 0.4. That would be our sample proportion. Okay, so we can use our sample proportion to make inferences about the population proportion. So let's start out first by talking about probabilities. So remember when we talked about means of a sample, we talked about what is the probability if we took a sample from a certain population, at a certain population mean, what's the probability that the sample mean is below some number, or the sample mean is above some number, or in between some boundaries. Okay, so we can do the same kind of thing with the sample proportion. Okay, so what we're going to do is we're going to take samples of a certain size n from a population that has a population proportion of p. And we do need to make an assumption here that the sample size is small compared to the size of the population. Usually the rule of thumb is that it's got to be less than 5% of the population size. And otherwise we have to use a correction factor, and that's not something we're going to do in this class. You can definitely take a more advanced statistics class and learn about that sort of thing. Okay, so as long as our sample sizes are big enough, then the sampling distribution of all the possible p hat sample proportions is approximately normal. So what does it mean to be sufficiently large? So here's a little formula. NP bigger than or equal to 10, or n times 1 minus p bigger than or equal to 10. When we get to an example, I'll show you how to do that. So basically it means if the expected number of individuals in the sample that have the characteristic and don't have the characteristic, if both those expected numbers are at least 10, then you're okay. Okay, so the mean of the sample distribution, so the mean of all the possible sample proportions, the mu of all the sample proportions turns out to be p. It ends up not being biased in one direction or the other, so you just end up with p. The standard deviation, It's not surprising there should be a square root, right? Because everything else we've done with the standard deviation has involved the square root. So we're going to take the p times the 1 minus p. And when you think the p and the 1 minus p, you may be thinking about probabilities. Because remember, the probability of a complement is 1 minus the probability of the original event. And sure enough, that's generally the same idea here. So basically the probability of the characteristic times the probability of the complement of the characteristic, and then divide that by n, and then take the square root. Okay. Then we're going to do a z-score. This should look kind of familiar to you as well. So this is the p hat minus the mu of the p hats divided by the standard deviation of the p hats. Just like means, what did we do? The sample mean minus the mu of all the x, so the x bar minus the mu of all the x bars divided by the sigma of all the x bars, right? So it's exactly the same idea. And it turns out when we do hypothesis tests with these, we're going to do them the same kind of way. It's going to be set up very similar to that. We're going to do subtract what we're comparing, and we're going to divide by the standard error, just like we do with means. So let's do an example. Okay, so according to the Census Bureau, about 35% of adults 25 and older have earned a bachelor's degree. So then, based on this, if we draw a sample of 50 U.S. adults, 25 or older, what's the probability at least 20 in the sample have a bachelor's degree? Okay, so the first thing we want to do is ask ourselves, are the sample proportions normally distributed? Okay, and so we need to figure that out, and actually, maybe even before we get to that, we need to figure out what is the population proportion. So basically, what is our characteristic of interest? So our characteristic of interest is that they have a bachelor's degree, right? And so then the proportion of population with the characteristic is going to be 0.35. Where does that come from? 35% of adults have a bachelor's degree. So we just take that 35% and write it as a decimal. So that is our proportion, and we're going to call this P. Okay, that's the population proportion. Okay? And so to figure out whether the sample proportions are normally distributed, we need to think about not just that 0.35, but also the complement of that. What proportion of the population that does not have the characteristic? Okay, so 35% of them have a bachelor's degree. How many of them don't? 1 minus 0.35, which is going to give me what? 0.65. So 65% of them do not have a bachelor's degree. So then to figure out if the sample proportions are normally distributed, I'm going to write that little formula here. So it's basically going to have, we need to have, and this is both, it's not either or, my NP at least 10 and my N times, 1 minus P. At least 10. Okay, so what's my sample size? So how big a sample am I drawing here? My sample size is 50, right? Okay, so my sample size is 50. And so basically what I want to do is I want to figure out how many of that 50 would be expected to have a bachelor's degree. Well, I'm going to take that 50, multiply by the 35%. And so that's going to give me, except I'm going to do this as a decimal, that's going to give me 17.5, right? Okay, and so then how many of that 50 would you expect if the population proportion applied to our sample? How many of those would you expect to not have the bachelor's degree? Well, you take the 50 and you multiply it times the 0.65, right? And so what does that give you? 32.5. Okay, so we look at these and we notice that they are both at least 10. And so what that means is that the sample proportions, which are, let me just write it, all the possible p-hats will follow the normal distribution. Okay, so that means we can use our normal table to figure out how many we would expect to have a certain proportion. Okay. Okay. So now what we're going to do is we want to look, but let me look back at our problem here. So a sample of 50 adults is selected, and they're asking what's the probability that at least 20 of them have a bachelor's degree. So that means we need to calculate our sample proportion. Okay. So this is the sample proportion that we care about. Okay. So this is our p-hat for our problem. So my p-hat is going to be x over n, so that's 20 over our 50, which is 0.4. Okay. My mean of all the possible sample proportions is going to be just p, and so it turns out that is going to be 0.35. My sigma of all the possible p-hats is going to be, here's my formula. Okay, let me go back and look at our formula here. Okay, so the mean of all the p-hats is p. The standard deviation of all the p-hats is going to be p times 1 minus p, there's our complement, divided by n, and then take the square root of that. Okay? So we're going to do p times 1 minus p all over n. Okay, and so then this gives me big square root, so this is going to be my 0.35 times my 0.65, and I usually just put them in my calculator like that. Instead of doing the parentheses, the 1 minus 0.65, I try to minimize the parentheses and just do simple calculations like that up front, outside of the main calculation. And I'm going to divide this by my sample size of 50. Okay, and so this turns out to be about 0.06745. Store this value in your calculator. You will end up off if you round to not very many decimal places in here. And keep in mind that when we're solving problems with proportions, all our proportions are automatically smaller than 1, right? So when you are rounding, you really need to go out to more decimal places, or you're going to end up off, and you may get wrong answers when you're doing your homework. Okay, so I actually don't cut it off even at that point. I just keep the whole thing in my calculator, and then I'm going to use it when I do my z calculation. Okay. Okay, this is my standard error. Okay, so remember when we had the standard error of the mean? This is the standard error of all of the set of all the sample proportions. Okay, so now we need to calculate our z. Actually, before we calculate our z, let's draw the curve. Okay, so our mu of all the sample the mu of all the sample proportions. So the mu of all the p-hats is right here. And what is that equal to? 0.35, right? Okay, so my p-hat of 0.4 is going to be to the right of this. Okay, now we're trying to find a probability, so we're going to be trying to find the area of some section of this curve. So let's go back at our problem and read it. What is the probability that at least 20 of them have a bachelor's degree? At least 20 having a bachelor's degree corresponds to the sample proportion being at least 0.4. So that means we want this area over here to the right. And we're going to be able to get that from the standard normal table. Okay, so what we need to do is we need to find the z-score that corresponds to that p-hat. Okay, so we need to find this. Okay, so how do we find the z-score? Okay, so my z, remember, is going to always be the value, so in this case the p-hat, minus the mean of all the p-hats, divided by the standard deviation of all the p-hats. Okay, so for us, what's our p-hat that we're interested in? 0.40. What's the mean of all the p-hats? It's just the population proportion, which is 0.35. And then we are going to divide by the standard deviation of all the p-hats, which is this 0.06745. So I'm going to write that in here, but I don't retype it. I use the stored value in my calculator. I'll store it like in variable A or B, and then I will use that. So I'll do the numerator, I'll hit enter, and then I will divide by that number. Okay. And so this turns out to be about 0.74125, and since our z-table only goes to 2 decimal places on the z-value, I'm going to just round it to 0.74. So this is a z-value, not an area. So we're going to go to our table. We're going to find the z-value for, what was it? I already forgot what it was. .74. So I find my z-value of 0.74. So those are the negative z's. I want a positive z. So I want 0.7 and then 0.04. So that is going to give me 0.7704. Okay. And so, let's think carefully about what area this is giving. And we can look on our picture of our normal curve here. So what are the areas in the table? These are all the areas that are to the left of the value. So that will give me the area to the left of my particular z-score. And then I can subtract from 1 or whatever in order to get the area that I want. Okay, so we're going to remember that 0.7704. So my area to the left of z equals 0.74 turns out to be 0.7704. So if I look at my sketch, I really want the area to the right, so that means I'm going to have to subtract from 1 because the area of the whole thing is 1. So the shaded area, which is going to be, this is going to be the probability that the p-hat in our sample is bigger than 0.4. This is going to be 1 minus that 0.7704, and so it's going to be 0.2296. That is the probability that I want. And so that means there's about a 0.23 probability that my sample proportion will be at least 0.4. Let's just rephrase this so that we know what we found. least 0.4, and that corresponds to the fact that at least 20 in the sample have a bachelor's degree. And so that's the information that we are after.